Hi everybody, and welcome to VSAONLINE. Slowly but surely, we are approaching the end of the 8th season, which is a great achievement in itself, I would say. And today I'm very happy to host two shorter talks. So I call this session a Blitz session on VSAONLINE. So we have two talks, one about permutations given by George Cynamon, and another one about memory from almost nothing by Stefan Reimann. So without any further delay, the floor is yours, Josh. So after your presentation, so we have a question session, short question session, and we continue with Stefan's presentation.
Okay. All right. Very good. Everybody, thanks for coming. So today I'm going to talk a little bit about permutations as another element of the VSA toolkit. I won't go into too much background about VSA's general operations, but let me know if there's anything that I say that's unclear. This is going to be primarily a method talk. I'm not revealing any big results today, although maybe hinting at some, I hope. So we'll talk a little bit about what a permutation is, and then we'll talk about some of the properties, how we can and may use them in VSA, and then you'll understand that fourth bullet point when we get there, and then I'll talk just a little bit about an application where we might use permutations to some advantage in VSA encoding. So permutations are quite simply operators that reorder a vector. They can be finite or infinite, of course, for our purposes, the vectors that they're reordering. For our purposes, we'll always be thinking about finite vectors, finite dimensional vectors. And there are three, at least, ways to think about what a permutation is. One is as a subgroup of linear maps from a vector space to itself. So if you think of endomorphisms from V to V, but they're always bijective, right? So each element goes to exactly one other element, which could be the original element itself, but there are no doubly counted elements. One way of representing these is as a matrix. You can see, I hope my cursor shows up. You can see you'll get a matrix with almost all zeros and n ones, and it's a little bit like the queens on a chessboard problem. You'll have 1, 1 in each column and in each row. And so the way this works is row 1 has a 1 in the 5th column, which means that the 5th value of your vector moves into the 1st position. The 4th value of your vector moves into the 2nd position, and so on. And a third way to represent permutations is as directed graphs. And so you can see here, element 1 moves to position 3, element 3 moves to position 5, element 5 moves to position 1. This sheds some light on the structure of permutations. One notation for permutations is what's called cyclic notation. And so I haven't presented it here, but you would see left paren 1, 3, 5, which tells you that the 1, the 3, and the 5 rotate with each other. Then you'd see right paren, then you'd see left paren 2, 4, and you'd see that means that 2 and 4 flip. Cycle notation is helpful for understanding things like the order of a permutation, how many times you have to repeat the permutation before you've returned to the identity element of the group of permutations. So properties of permutations. Again, I haven't noted this, but the permutations form a group under a multiplication operation, which is function composition. But in the context of VSAs, the permutation has a couple of nice properties. As binding distributes over superposition, so too does permutation distribute over both addition and multiplication, or both superposition and binding. Another key element of how permutations work is what I'm calling here orthogonalizing, in the same way that if you take A and B and bind them together, the resultant vector is orthogonal to A as well as B. If you take a vector and an arbitrary permutation and apply the permutation to that vector, you'll get a new vector which is perpendicular to your, or approximately perpendicular to your original vector. And in general, you can repeat this process over and over and over. What I haven't noted is it's actually rho applied k times to V is orthogonal to rho applied j times to V, provided that k and j are not the same. So I note more on this later, because this isn't always the case. And if we choose for it to be not the case, we can be very specific about how much we don't want that to be the case. So in other words, where an arbitrary permutation applied to an arbitrary vector will be perpendicular to the original vector, we can choose permutations deliberately such that the permutation applied to a vector is as far or as close to the original vector as we would like it to be. And there may be some useful situations where we want to do that. So the role of permutations in vector symbolic architectures, I'm going to focus on the role as I've used it. That's not to suggest that there aren't other roles. It is helpful for indicating directionality. So we all know that if you have A plus B, we can't differentiate that from B plus A. We know that if you have A bound with B, we can't differentiate that just as it is from B bound with A. And permutations afford us the capability to differentiate. So you can have A bound with permutation applied to B is going to be different from B bound with permutation applied to A. And this is pretty fantastic because it allows us to do things like encode directed graphs. There's also some applications for ordered lists. I'm not going to get into that, although I know there are folks on the call who have used these in that way. But this is just to indicate to anyone who hasn't seen this, the way that you would encode a graph as a vector. It's a superposition of bindings of permuted vectors. And so we would have our vector associated with vertex v1, vector associated with vertex v3, v2, and v4. And the way that we would combine them to represent the overall graph is v1 is the beginning of the directed edge ending at v3. V3 is the beginning of a directed edge ending at V2. It is also the beginning of a directed edge ending at V4. V2, directed edge to V3, and V4, directed edge to V1. And so by encoding the graph in this way, we can subsequently pull out information about the graph, such as which vertices can you get to from a given initial point. There have been a couple of different approaches involving different uses of bundling and binding for these encodings. So here I'm using a binding for the edge and then a bundling to combine all of the edges. Some folks have endeavored to do this a little bit differently. For my purposes, this was a good way of doing it, but I'm interested if folks have points of view on the nuance of which way is most useful and most effective. So I talked about this orthogonalizing idea. So if you take an arbitrary permutation and an arbitrary vector, you'll have this property that applying the permutation a finite number of times, and there's a number that's too big and you'll run into trouble, but effectively, as many times as you like, you'll continue to get orthogonal new vectors moving through space into random unrelated positions. That needn't be the case if you choose your permutation deliberately. And in particular, talking on this idea of cycle notation, I think most of us think of a permutation as being a single n endpoint cycle. So perhaps 1 goes to 2, goes to 3, goes to 4, dot, 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 goes to n-1, goes to n, which goes back to 1, or some other similar shuffling. But you can actually have as simple as 1 and 2 flip, 3 and 4 flip, 5 and 6 flip. Well, for that case, you certainly don't have this property. The single permutation of the vector is going to be perpendicular to your original vector, but a double permutation actually gets you back to the original vector. And you can imagine if you had one cycle which completely shuffled half of the values and all of the other cycles were these 2 cycles, then you'd get a characteristic where one application gets you a random orthogonal vector, but 2 applications gets you a vector that's 75% in agreement with your original vector. And again, we can play games with how much or how little agreement we want. And there are a few concepts, I'm sort of giving a nod to them. We don't need to go into detail. There are a few concepts that come out of abstract algebra as applied to operators on sets for group actions, where you can say things like, if I take a permutation, how many of my vectors are going to be fixed by this permutation? If I take a permutation, how many of my vectors will be partially fixed by this permutation? If I have a base vector and I apply any of my permutations to it, what vectors can I get to? So for example, if your vector is 1, 1, 1, 1, 1, dot, 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 that's the only vector you can get to. You can shuffle those values all you want. You're never going to get a 0. But for different vectors, if you had a vector that's 50% ones and 50% zeros, you can get to many other 50% 1 and 50% 0 vectors. And in fact, if you're exactly 50-50, you can get to all of them using permutations. And then there's, I have this similarity. This is not a conventional notation. I don't know that there is a conventional notation, but if you take a permutation and then you pick a vector and you say, how does the original vector compare to the to one permutation of the vector, the original vector to 2 permutations, 3 permutations, etc.? How similar will those be? And I think Dimitri has done some work in this area, although I think he and I have taken a slightly different approach about which permutations we pick to look at. But we've been talking a bit about our respective approaches. In particular, you can choose permutations that have very different shapes of this similarity array, right? So if you choose your permutation to be the identity permutation, these will all be 1s. If you choose your permutation to be a completely random permutation, an n cycle, these will be, unless you're very unlucky in the vector you choose, these will all be approximately 0.5. But you can choose a permutation which fixes half of the points in your vector and cycles the other half. And again, then you'd have 0.75, 0.75, 0.75, and so on. And you can be, you have a lot of latitude in what the shape of this similarity array is going to look like. So I wanted to approach using these permutations in order to try to create a certain effect on a graph that I had seen previously in work by Melanie Mitchell and Douglas Hofstadter in their copycat project. And in particular, they had a concept graph. It was a mostly undirected, although some of the edges were effectively directed edges, graph, which connected all of the relevant concepts for their copycat model. And during the course of a copycat run, this graph would deform in order to accommodate the model processing that certain concepts should be closer together than they would be all things equal. That something about this run of the model suggested that these concepts, that oppositeness is important. So concepts which are opposite should be closer together. Or that likeness is important. So concepts that suggest similarity should be brought closer together. So what this effectively did was take edges, certain of the edges on the graph, and shrink them and say, okay, so normally A is equidistant to E, B, and C, but now we're going to have A be closer to B and equidistant to C and E. And I'm sorry, this doesn't illustrate it very well. It's hard to show in a cube that your depth line segments are the same length as your other line segments. I haven't come up with a great way to represent that. But the way I approached this was I said, suppose your each Cartesian coordinate represents a certain flavor of connection. So you could think of it as left to right is size, up and down is shape, and front and back is color. And so we encode the graph in this way. The link from A to B is going to be row 1 applied to A cross B, or A bound with B. In this case, sorry, I should clarify. So this looks a little different from our directed graph because this graph is assumed to be undirected. So we're treating it as though A and B are connected by a vertex, but it's not directional. So in this case, binding them first and then applying the permutation is just fine. What you get is your full graph is going to be the sum of all of these 12 permutations. But if you choose row 1, row 2, and row 3 thoughtfully from your group of permutations, you'll get a property such that applying row 1 to the graph will shrink these edges, but not these edges. And it needn't be that it shrinks these edges to 0. It just makes A and B a little bit closer together than A and E are, or than A and C are. And further, if you choose the permutations carefully, row 1 of A bound with B is going to be enough similar to A bound with B that if you unbind it with A, you'll get B back. And so that's another important characteristic here. And so what I was able to demonstrate in a very basic, very in some sense artificial graph is that you could replicate this deformation of concept space by using permutations in order to bring certain concepts closer together without bringing others closer together. And this was started as work with Pentti Kanerva, which was originally exploring more generally the nature of permutations as applied to VSA, and then in particular creating a sort of metric for permutations and whether we could apply that in the copycat model. But I think it has uses more broadly than just copycat. And so that's about all I wanted to say as my opening salvo. I think I've come in under 20 minutes, hopefully not enough under 20 minutes that people feel cheated.
Thank you, Josh. Let's see.
Thank you for having me.
If we have questions or comments. Well, actually, I have comment, maybe not very deep comment, but rather response to your question about different ways of representing graphs. I mean, which method is better or than the other? Well, it really depends on the use case and what you want to. I mean, which part of which aspect of the graph problem you want to focus on, and maybe as a kind of teaser. So maybe next season, so we will have a talk where we will shed some light on different possibilities of encoding graphs. But this question is really interesting, and I personally found very interesting this use case that you presented about preserving different similarities between edges. So that's really cool.
Oh, thank you. Yeah, it was neat. You know, when Pentti and I were first talking about it, I guess it's probably natural to find it hard to get your head around n factorial when n is big, but it really took a while for it to sink in just how big the group of permutations is in a hyperdimensional setting relative to the size of the group of vectors for, say, binary vectors. Right, 2 to the n grows really stunningly less fast than n factorial, which I'm sure all the computer scientists will be sort of rolling their eyes and groaning and thinking, yes, of course it does. But it's really striking when you look at specific values.
So let's see.
I would have a question.
Yes, please.
Oh, sorry.
Go on, go on.
Yeah. You will not be surprised after my talk. What I found very interesting is if you have a vector, then by applying a particular permutation with some properties, you will create another vector having a particular distance from the first one. So if y is the permuted x, what then is the normed Hamming distance between x and y? What properties should this permutation have in order to establish this distance? Can you answer that in general?
So I can probably initiate evasive maneuvers and try to dodge the question. So I think in general, it depends what you're trying to accomplish. But your question is, if I understand it correctly, you're saying if you take an arbitrary permutation, what would the similarity be? Or you're saying for a given permutation, can I tell you what the similarity would be?
No, for a given vector, how must the permutation be so that the permuted vector has a particular distance from this vector?
I see. Okay, so in general, if you have a vector that's the vectors I think we all pretty much tend to work with, which are approximately equal numbers of zeros and ones, almost any permutation will give you a resultant vector that's close to orthogonal to your original vector, unless you deliberately choose one that's not. And I guess that depends what you mean by how close and how probable. So 1 over n of your total possible permutations are n cycles. So in that case, they will completely shuffle your vector and you should get something that's roughly orthogonal. 1 over n minus 1 of your permutations are an n minus 1 cycle and 1 fixed point. So that one will again be very close to 0.5 similarity. But there are very many.
But okay, then you simply have to determine the cycle length, huh?
You need to determine the cycle length, but you can be a little bit sneaky in doing things like if you want even numbered iterations to be similar, but not odd numbered iterations, then you choose a lot of 2 cycles. Or if you want it to be a bit smoother, you can say, well, I'll choose a quarter of my values will be in 2 cycles, and a quarter of my values will be in 3 cycles. And so then one application gives you a vector that's perpendicular, but 2 applications gives you a vector that's roughly 2/3 similar. 3 applications gives you another vector that's roughly 2/3 similar. 4 applications gives you yet another vector that's 2/3 similar. And then on your 5th application, you'd be back to being perpendicular. But you can, by playing games with the relationship of how many points in the vector are in each cycle length, you can shape the contour of that similarity array.
Okay, thank you very much.
Sure. Thank you.
Let's check if we have more questions. Ross, you...
Yeah, thanks very much. That's really interesting, Josh. I just wanted to make a notational comment. I mean, I think a lot of the work that's done in VSAs uses permutations at all tends to notationally just put it down as a pi or something or other. But it sort of implies that there is only one permutation, whereas what you're doing here is you're saying, no, there are all these different permutations and they can do different things. So I think it would be really helpful to, when people use permutations, notationally, put a subscript on them so that this is just one of the range of possible permutations you might have.
I'm gratified to hear you say that. I will, at risk of sounding like I'm sucking up to Penty, he really opened my eyes to the idea of there being a lot of variety in the permutations, and I do think it's striking because, as you say, often if you read a paper in our field, someone will talk about taking a permutation as though it couldn't make one bit of difference what that permutation is. And it turns out that if we want it to make a difference, it could make a lot of difference. So
yeah, I think the other point which is interesting is that as far as I'm aware, permutations, I mean, the way that permutations would be used in the field is essentially static, in that, you know, the mental model is, you know, it's a piece of hardware sitting there. They're doing this one specific permutation
That's
that
right.
you've chosen it to do, which is interesting. I mean, because if you look at the addition and multiplication operators, yeah, sure, they're binary operators and they're not subscripted because, you know, they just are what they are. But you can also think of them as curried functions, where you're thinking of it as a unary function that's parameterized by one of the two arguments. And so you can choose the the curried addition or the curried multiplication on the basis of the argument, which is just a hypervector, so it can dynamically evolve. But
yeah, no, exactly.
There's no dynamic equivalent of, you know, a parameterized permutation where you could represent the permutation by a hypervector.
Yeah, and I don't want to pick any fights, but I think you treating the permutation as a static operator is a little bit like using your computer as a 4-function calculator. It just leaves a lot on the table. There's so much richness that you can work with, and you're foregoing all of that if you treat it as though it can only be used in this one way.
Okay,
I mean, which isn't to suggest that it's not also, you know, very, very useful in that specific way. It's just that I think there's quite a bit more that it can be used for.
Yep. Thanks.
Yeah, thank you.
Tony, you unmuted yourself.
Yeah, really interesting stuff, Josh. I'm very curious to see what you can do with these. The copycat, that was one interesting thing I'd love to see more about. But I was thinking about that. That's an interesting observation. I hadn't thought about it before, that there's many more permutations of the elements of a binary vector than there are different vectors. And I was thinking, how could that be? Well, it's obvious. It's because shifting a permutation may not actually make any change to the value of a vector. It just shifts the ones to where ones are and zeros to where zeros are. And so that makes me think, can you say anything about like how the density of the vectors, or anything else about the sort of some abstract quality of the patterns of the vectors interacts with the effect of, you know, how much a permutation will actually change a vector?
Yeah, so I can say a little, but I quickly get out over my skis. I don't want to commit things where I'm out of my depth on it. But in general, if you're with most permutations, and we should sort of characterize what we mean by that, but with most permutations and most vectors, you'll get a pretty good shuffling. But for any given permutation, there will be a bunch of vectors which sort of fit that permutation very nicely. And you can set thresholds. You can say, well, what's the size of the collection of vectors which have the characteristic that one application of the permutation returns your original vector? And what about one application returns a vector at least 90% similar, at least 80% similar, at least 75% similar, and so on? If you have a permutation that's randomly picked out of the bag of permutations, the sets but on the other hand, if you choose your permutation so that, for example, it fixes the first half of your values, then all of a sudden you're going to have lots of vectors which aren't, you know, which don't move around very much. And you'll even have a bunch which don't move around at all. Depending on what the non-fixed half of your permutation looks like. But having said that, I can't give you a sort of a magic machine for saying, what share of your vector space, the probability distribution of which vectors will be a certain amount similar when one iteration or multiple iterations of the permutation are applied.
Okay, thanks.
Sure.
Thank you, Josh. I think we now will swap the speaker.
Oh, very good. Here, I'll release the screen share, I think.
Thank
I
you
can figure out.
for your part so far.
Oh, thank you. There we go.
So now we move to Stefan. Maybe you need to unmute. Yes.
Sorry, I always forget to hit the button. Okay. Is it visible for you now?
Yes.
Good. Wonderful. Josh, you will see I enjoyed your talk a lot, and you will see in particular why I did that. So,
Thank you.
since this talk is supposed to be short, I should start at the ending. And the ending is the following. Oh, should work? Yeah. What you see here are real data from memory experiments. Briefly, most of you will know what it is, but I will recapitulate it anyway. Participants are given a sequence of items they have to remember. Maybe there are 15 items or there are 10 items. And so you see in the x-axis the serial position I. And these participants are asked to recall items from these lists in arbitrary order. This paradigm is called free recall. And here on the y-axis, you see the accuracy or the frequency or the portion of correct answers. And then you see that typically these curves are asymmetric, they are U-shaped, and the right portion on here is then called recency effect. So the most recent items are best recalled, and this here is called the primacy effect. So those elements on the very beginning on the list are also very good recalled. Here, these ones in the middle, no, not really. And these curves typically look like that, not only for humans, also in an analog setting, also for animals. You cannot only use free recall paradigm, you can also ask the participants to recall items from the beginning to the end or from the end to the beginning. And then you again see such curves here. This is again the serial position number. And here you have the accuracy or the proportion to be correct. And here, this is, they were asked, okay, tell us the very first items first, and here tell us the most recent items first. These are very typical data from memory. And here is now the generic behavior of the model I would like to tell you. You have seen similar figures already, because this is something I've been thinking about for some time. But what I would like to stress here, you get precisely this kind of asymmetric U-shaped curve up as a generic behavior of the system. And with one parameter more, you also can mimic these different paradigms. And now let me tell you how I did it. The first thing we would like to have, and this is quite usual, we would like to have the presentation of an object. And this presentation is high dimensional, and this is called a state. You can simply you can say, okay, this is a kind of visual field, quadratic grid, and each field there is either active, and it is white, or it is inactive, and it is black. And then we have a 2 times do activity field. This is what I call a state, and you can of course make a vector out of it. And what we now here need, and here we have a representation mapping. I will come to this in a minute. And what we need is a kind of abstract property of this field is the mean activity in this field. This is only really the mean activity. The mean activity is always called Q, and this is the field. So the only thing I require from this representation is that it is in some sense continuous. So the idea is that similar objects like U and V are mapped to nearby states, having a small Hamming distance in this case, while those objects which are not too similar, like V and M, are represented by states which have a quite big distance. So this, the only thing I assume is that I have this representation, and this representation mapping is in some sense continuous. And now the question is, how much does one state represent of another? And as I said, here I have a state X, and this corresponds to this field here. And this one can now be understood as, I don't know, n times n realizations of one random variable, which with some probability Q takes the value of 1, and with 1 minus Q is 0. So I consider these states as representations of a random variable. Here are 2 examples. What I now can do is, if you have the idea, well, we would like to employ mutual information, then you would like to talk about the joint probability distribution of these 2 states, X and Y, where this X there has a mean activity of Q. This is simply the probability that components are 1. And Y has a particular distance from it. Josh, this was now precise the background of my question. I would like to control for this distance. And now I draw the joint probability distribution. So the first element in this matrix simply says that both components xi and xyi are both 0. Here both are 1. Here it is 0, 1, and here it is 1, 0. This is simply the joint probability distribution. Now you can calculate the mutual information. And now something, for me, strange happens, and this is true what I say, but it is only brute force calculation, so it is not really understanding. What turns out, what you see here is, here you have the determinant of the joint probability distribution. This is this one here. And here, these are simulated points, these stars, while these dashed lines are an approximation, and this approximation is simply determinant of the joint probability distribution squared. In higher order, in lowest order, higher orders go with order 4, 6, 8, and so. But as you see, the approximation is quite good. you can now go a little bit further. You can introduce binding between two vectors in a very simple way. As I guess it is component-wise applying the XNOR operation. So x times y, the east component of x times y is equal to 1, even if both components are the same. So therefore, if we have an x here with 0, 0, 1, 0, 1, 1, and the y over here, you have here a 0 in binding, here you have a 1 from binding, here you have a 0 in binding, a 1, and so nothing great happens. This is the binding operation I consider. And what then shows is that this factor here, the determinant of the joint probability distribution squared, equals the mean activity of the two states bond to each other, okay, minus 1/2 squared. This is precisely what you see over here. And if you now go one step further, if you have such two states of two objects and you bind these objects together, then the squared activity of this bond state somehow relates to the mutual information between states U and V. This is simply something I've shown here again. So now you have for me, a very surprising connection between binding two binary states together, looking at the activity and the mutual information between these two states on the other. So if anyone can help me understand this problem apart from calculating this is done, I would very much appreciate that. Because in particular, this says that calculating mutual information in very, very simple systems is possible. You do not need a log. You do not need anything very complicated. You have in the definition what mutual information is. In some sense, you only have to count, and this is something I found surprising. It seems to hold for states which are not binary but also have minus 1, 1, and so on. And but it seems to relate to the high dimension. Let's see. Honestly, I don't know. If anyone has a good idea, I very much appreciate that. Good. Now, we spoke about binding, relating this somehow to mutual information between states. But now comes something which is more important for me, or more, this is the following. I have a sequence, X, Y, and Z, and I would like to represent this sequence. And usually, as it is done by bundling, and this bundling is a kind of vector like addition, and you have, first you read in X, then you have X plus Y, then you have X plus Y plus Z. But because vector addition is associative, you end up with that this is equal to Z plus Y plus X, and this goes for the sequence Z, Y, X. So both sequences are the same. If you have an associative bundling operation, it will not accept or respect sequence information. What you then usually do is to add additional structure. Either you say there are serial position markers, so 1 is bound to X, 2 is bound to Y, 3 is bound to Z, or you can employ something which is chaining. This is a little bit like what we have seen now in the graphs, that X is bound to Y, Y is bound to Z, and then comes Z. Or you can do it as it is often done here in VSA. You can code the sequence by powers of, in this case, then random permutations like this. So this is the most recent one. This is the one before. This is in the beginning, and this simply codes for that. But if you think about what this kind of operation is, this is rho times x plus y. And what is this addition about? And what you see here, if you calculate a applied to x, applied to a, y, z, this is simply checking for associativity. You obtain this one, which corresponds to this one here over here. This is fine. But the other side corresponds to this one. And these two things only are the same if rho is trivial, either 0 or 1. So you have a non-associative bundling operation here coded by this idea that sequences are coded by powers of permutations. And from this came the idea to say, okay, if we can code sequential information by non-associative bundling, then simply think about a bundling which is not associative. And this then came out as an idea. First, have a look over here. The idea is oh no. Assume you have two states x and y here, and you would like to bundle them together to give a third state z over here. And you do this in a way, component-wise, if both components are 0, you give a 0. Give it a 0. If both are 1, you give it a 1. But if only one is a 1, then with some probability, a 1 will be chosen here or not. In other words, if this kind of threshold here is 1, then this bundling is component-wise AND. And if this threshold here is 0, then bundling is component-wise OR. This was the idea. So to inject at any stage where you bundle two things, some noise into the system. How can this be done? Well, very simple, or not too simple. You can think about the perceptron having two entries x and y here, and depending on some thresholds, it will be either activated or not. And you can also write this then, of course, as a perceptron which simply has a random input. And this is what I called an embedded perceptron sitting in a Heath bath. So, and the biological intuition behind is we do not only have neurons which are connected to each other, all these neurons are embedded in a huge glia network of non-neural components which activate and also input in the background. This is so more or less what we see here. So by these embedded neurons, we have done an addition or a bundling, which is in fact not associative. So only, and this is now in particular for Tony, we can compare this bundling operation and the binding operation here. What we do here, we look at the typical normalized Hamming distance between states x and y. And the first little observation is that the Hamming distance between x and y is nothing else than 1 minus the activity of the bond state x times y. This is a nice, well, this is not even a result. It is nice to observe because it really simplifies all these calculations. But more importantly, what then comes out is that bundling creates similarity, while binding creates dissimilarity, and this is precisely what we want. What we want to have. The point simply is that this dissimilarity. oh, this is something I should mention later. So now we have a kind of algebra. We have states, we have bundling, addition, and we have binding, multiplication. It's nice algebra. And now we can put states, we can bundle states together, maybe infinitely many. Could it be that bundling infinitely many states together will end up in a state which is either one, only consists of ones, or is only zero over here? This is a kind of catastrophe happening, right? And in fact, what you can show is no. If this threshold here is away from 0 and 1, so if the bundling is really not associative, the mean activity of this state here will asymptotically, when the sequence of words bundled together becomes infinite, converge to this number here. This is precisely what you see here. We start here from a state having activity 1/2, and depending on the threshold, the activity decreases if the threshold is larger than 1/2, but asymptotically it will go to this, and this one will always be either larger 0 or less 1. So when you use this non-associative bundling, this kind of catastrophe cannot happen. There's even an infinite number of states being bundled together gives you a completely state without any information. So therefore, we can create states simply by bundling. This is now something what happens. We start from an initial state, might be empty, might be random, might be something. And the first element we read in is the x. So what we do, we bundle the x to the initial state in order to get out this one here. The next one is we now bundle with y, but now we have a non-associative operation. So therefore, we have to distinguish between left associative and right associative. They are not the same. So therefore, we have a vector L2 and we have a vector R2 corresponding to right and left associative. The same is, of course, if we apply then the bundle to it the third element, which is Z, giving you this L vector and this R vector. Therefore, what comes out, if you think about non-associative bundling, this sequence is not is represented by a vector x here, but this vector has two components, and this one component corresponds to left associative bundling, and the other one corresponds to right associative bundling. So and now, okay, you have now memorized a sequence. And now you recall, tell me whether X has been the sequence or not. So what does your representation of the sequence large X represent of your little x? This is the question we had in the very beginning. This is something we answer by regarding considering the mutual information. And since the vectors R and L both contribute, I say, okay, the mutual information, which is of course not really a linear something, but the mutual information or mutual information between capital X and X equals the sum of the mutual information of the R vector and the X and the L vector of the X. And this is precisely what you see here. This here is the L vector. This here is the R vector, and this is simply the sum of both. This is the reason why I call this a generic behavior. And here you see the results from free recall. In here, you can say, oh, well, maybe the influence or the importance of the R vector is bigger or smaller than the influence of the L vector. So you can weight these two. Okay, and now you can play around with this alpha. The alpha prime for me usually is 1 minus alpha, but this is not necessary. And then you simply obtain these two curves, which again nicely correspond to this one here. So this is the entire magic behind. So for me, not too much happens. Last little story is about, okay, I said it is nice to have this non-associative bundling in order to represent sequences. But does this somehow correspond to anything? And then I saw the following, which is maybe only a kind of storytelling. Depending on whether you lesion the hippocampus or you put the patient in a state of amnesia or something, it can really happen that either the recency effect is impaired or the primacy effect is impaired. Here, for example, this is in rats. Here you have a hippocampal lesion, and here you see that the primary effect is impaired. So in my reading, within this theory, it simply means that therefore that these L and R states, they are in some sense independent of each other, or they can be constructed independently of each other. And this is all the existence of L and R state result from the non-associativity of bundling, and this may correspond to something you then also see in memory experiments. And with that, I thank you very much for your attention. Thank you.
Stefan, thank you very much indeed for your talk. I brought so much new information for myself out of it. Thanks. So do we have questions in the audience or comments? Maybe just to begin with a simple question to clarify the notations. When you say when the left and right superpositions are combined into a single vector, so is it concatenation or you're talking about, or it's more of a tensor here you start to, or a matrix?
No, it's simply this one vector simply has two components. It's like in quantum mechanics. This state of the object can either be in the up state or in the down state. In some sense, it is a little bit like this. So these are really two components of this one vector. You could also call this x1 and this one x2.
Okay. But I mean, L and R, they are two vectors, I mean, according to the upper notations, right? I mean, they're just vectors
precisely
by their own.
And the interesting thing is so here in the very beginning there is the same.
Yeah, of course.
Yeah, they are also and then they somehow diverge.
Yes,
and it is really the case that if you have an infinite number of things to bundle, these two will become orthogonal.
Yeah, absolutely. Mm-hmm.
And the reason for this is intuitively very simple, because at any bundling step you inject some noise, and this noise is accumulative, and so therefore in the very end you have really two orthogonal vectors there, and then L and R will be orthogonal to each other.
I see. All right. Mm-hmm. So let's check the audience. All right. Tony and Ross,
Yeah.
expecting you
Yeah.
to unmute yourselves.
So yeah, it's very interesting. So when you're building up your composite memory vector here, it looks like it needs to be, if you think of adding something new into the existing vector to for a new element in the for the next element in the sequence, it looks like you would have to build it up in both directions. It's not like there's a simple recurrent operation, is there?
That's true.
Yeah. Okay.
And I've thought about this problem for quite a long time. One, I guess it is the I don't know, either the L or the R vector. This is a very simple iterative something. The other one is not. And this was, of course, a little bit annoying. First of all, it is only about something computational. It's not about how it is really realized. This is one thing. Finally, you get some vectors which code different orders. And you can, I absolutely admit, for me, it is not clear how to realize this in a simple mechanical way, except you have this this vector coming down here, one goes into this direction, and the other one first goes into this direction, then a swap over here. So I admit this is a formal calculation stuff, and I cannot really say how it can be realized, unfortunately.
Yeah. Another question on that was really interesting that you showed that as you do repeated application, that it doesn't go to all, that it doesn't saturate at either all zeros or all ones. And your little plot there shows it converging on 0.8 and 0.2. Yeah, so that surely depends upon the other parameters of the system, right?
Yes, precisely. Sorry, what I have forgotten to write in here, this 0.8, this line here is precisely this value here.
Okay.
If you calculate this for q equal 1/2 and tau 0.2, then you will get 0.8.
Yeah.
This is precisely the this value over here.
Yeah, makes sense.
Ross, please.
Yeah, thank you. Stefan, actually, Tony, I was just about to, I think that the point I want to make will actually also speak to that. Stefan, I think it's the previous slide. If you could go back one. No, the one where you've got the, you show the implementation of, excuse me, bundling with the matrix and the probabilities in it. That one, thank you. Yes, okay.
This one here.
Yep. Let's just make an observation about this, which might help in interpretation and also does say something to that second question that Tony was raising, that you can implement bundling, associative bundling. Well, depends how you think about it. You can implement a bundling as a component-wise random selection from the vectors. So basically, if you're doing a 50-50, a standard bundling, you're just selecting each element at random from one of the two arguments. If it's a two-argument bundling, so you choose, etc. So then, in that case, this equivalent matrix here, the probabilities, the off-diagonal probabilities, well, when both argument elements are 0, then obviously it doesn't matter which one you choose. You're still going to get a 0. Ditto, when both argument elements are 1, you're going to get a 1. So the random part only affects what happens when they disagree. And that random selection bundling, the probabilities would be p and 1 minus p, rather than the same p for both, as they are here. So one interpretation of what you're doing here is, rather than choosing between source arguments with a particular probability, you're choosing between values with a probability between the two different values. So essentially, you're implementing a value-dependent sampling. So it has a preference for a higher value or a lower value, depending on how you set your parameter, which is then presumably
depending on how the theta is. Yes, precisely.
Yeah.
Maybe
so then,
sorry, just I mean, napping on your definition. How did you put it? Context-dependent sampling, or what was it?
Value-dependent sampling.
I think in Dimitri's term, it's context-dependent thinning. So that's what the
yeah, that's probably right. Yeah. So it's okay. No, I'll just jump out of the conversation at that point and leave it to Dimitri. I was just going to say that explains, I presume, explains why you get those asymptotic curves, because you're showing a preference for a probabilistic preference for higher values or lower values on the contestable items.
Agreed. And Ross absolutely agreed. And the idea really was thinking about this kind of perceptron here, receiving 2 inputs, and then depending on the threshold, it either goes to 0 or it goes to 1, precisely what you said. This is this entire modeling idea had something to do with this kind of perceptron picture. And what you mentioned is another mechanism. That's true. And the only thing I wanted to say is this is one of the bundling operations which is clearly not associative. One can understand quite well why it is not. There are others which might or which might not. I do not know whether the bundling operation you suggested is associative or not. I don't think so, but this is another one.
No,
why not?
Yeah, no, I don't think it is associative in that, because you've got the fixed magnitude of the vectors. Essentially, if you can only do a binary bundling, then the further the thing that goes in first effectively gets eroded away at random over time. So there's very little of it left in the sum. Anyway,
sorry.
Thank you for that.
What I only wanted to say is one now simply has to really check this one. And of course, there are many operations which are not associative, and so therefore not associative bundling, I guess, is not exotic. And it has really advantages from my point of view.
Indeed.
Thank you. Thanks for the suggestion. I would check it.
I just it came to me that if you go back to this probabilistic superposition again, yes, I don't know if it makes sense.
This one?
No, I mean with the matrix. I mean where you have this theta or whatever. Yeah, this this definition.
Yeah.
I mean, you're working with memories, and again, I don't know whether it is relevant or not, but I remember in the context of self-organizing maps, so this long Cohonen maps, in the middle of 2000, so there was a work on binary or ternary self-organizing maps. So basically, this work was about just hardware efficient realization of SOMs, and they used this operation actually to kind of form the memory in each of the SOM cells. So I don't know, again, so this is just a reflection. So and I don't know how much of use this information is for you, but maybe like extending.
Let's see.
Extending. I mean, this observation on kind of more generic memory, like concept, like memory maps. So
Yeah.
that can be. I mean,
now, of course, when I'm here talking about perceptrons, and Corona also did that in a slightly different way, it would be interesting to see the connections between the two. Yeah, that's true.
all right.
May I
sure.
only again ask, simply here, so many brilliant people. I was astonished when I saw this immediate relation between mutual information and so more or less Hamming distance. In high dimensional systems, it seems to be the case, at least in binary, that you can approximate mutual information by counting Hamming distance. Because this Q here is nothing, this one you can also write as the Hamming distance between x and y minus 1/2. This is precisely the same. So therefore, Hamming distance between x and y equals the square of the, mutual information between x and y equals the square of the Hamming distance. I found this very surprising. It is okay when it comes to calculation, but in particular, this connection here, that the mutual information can be approximated by the determinant of the joint probability distribution squared. I don't understand. I can calculate, this is absolutely fine, but I don't understand where really the connection between these two things are. And as I said, I'm really asking for some understanding or help here. It is not about numerics. This is absolutely fine, but maybe it is something absolutely obvious, and one of you can explain it to me. This would be great. This is almost my question.
Could I jump in?
Please.
That term in the middle there, the QXY minus 1/2. So that's basically a linear rescaling of the Hamming distance.
Right, precisely.
For binary systems, that's how you calculate the cosine similarity from the Hamming distance. I mean, they're isomorphic.
Yeah, sure.
So that's just the square of the similarity. And that's perfectly sensible, because there's only one way to be exactly the same, and there's only one way to be exactly in the opposite direction. So I think
Ross,
so qualitatively, whether that saying that that's exactly the same as the information is far beyond my ability. But I mean, it's just qualitatively. The combination of that's basically similarity squared, because that tells you how constrained they are by each other, and concentration of measure, saying that when your similarity is 0, there's just a vast number of ways you can be different, completely different.
Right. Now, and Ross, I absolutely agree. That there is, if you have two independent variables, then your joint probability distribution is diagonal. And so therefore the determinant is 0. So is the mutual information. And the same is true then and also for the distance. All these things, conceptually, all these things fit together. Maybe there's nothing more behind that, but I only found it interesting that, because for me this simply shows we at INI, we are working about very simple mechanistically realizable neural systems, somehow neuromorphic ones, And if I do something simple, but then suddenly I need mutual information where I need a log and all of these strange things, this is horrible, because this is a very complicated thing. So how can I, in a very simple way, calculate mutual information? Here it shows off that it is nothing else either than the square of the activity, or simply a Hamming distance. This then is simple enough. And
from a practical point of view, you might not even need to have the mutual information. So as long as that the square of the similarity is the mutual information, as long as it was monotonically related to, is probably be perfectly fine for practical purposes.
Another fun fact, which is Ross, you mentioned correctly, it is nothing else than the square of the cosine similarity. So it is more or less a kind of projection. And if now these two vectors were normalized, it is nothing else than a probability amplitude. You know very well from quantum mechanics. Comes out of that. I don't know what it is. Simply finding strange things.
So we have Pentti and Josh wanting to comment something.
I just had a quick question. Does it bear on how you interpret this? What the likely distribution, what the likely density of your vectors is? I mean, if you were to say I have sparse vector, or I have sparse representations, then agreement between two ones means a lot more than agreement between two zeros. It tells me a lot more, right? So the mutual information isn't really accounting.
I guess you refer to this one, right?
Yeah.
Joint probability distribution. Okay. And the Q is the probability for a one. So therefore, if you have a very dense state, the Q is close to 1/2. Otherwise, it is either close to it is close to 1. If you have something very sparse. So this is what is written here. This is so more or less the sparseness of the vector X.
Yeah.
This is this Q here.
Yeah, it just occurs to me that if you have so if, say, 50 of your 10,000 values or 1,000 values are likely to be ones, then you could have two representations with similar Hamming distance, but with, you could have three representations, and pairwise they have similar Hamming distance, but there would be one pair that we say, oh, this is very clearly much closer than this other pair. Or I think maybe I'm not saying that correctly, but I think we would. I'm trying to think.
Maybe you should write me an email about this.
Maybe I should write that down. Yeah, maybe I shouldn't get ahead of myself on that.
It would be helpful.
Yeah.
Yeah, I guess somebody already said that this is about the mutual information as square. If you take the Spearman correlation and square it, that explains how much of the variance has been explained. I mean, there's how much the variance of one the other one explains, and so if there's something I learned in statistics long ago.
Yeah.
It's very nice.
So all ideas are welcome. It is maybe this is something in the direction of what Yevgeny once called the magic of high dimensionality.
Did I say it?
Yeah, you did.
I think it was Pentti in the beginning.
Okay. Anyway.
Okay.
Yes. Listen, I think.
But thanks, Pentti. I will think about this. Yeah.
I think we did really great, and we had a very great discussion. I mean, for the concluding session of the webinar. So the only thing it remains to be said is that thank you all for being attentive and attended all of our sessions, and so we hope for the new exciting season. So I will send a separate announcement. So we are working on the program as of now. And so once again, I would like to thank today's speakers, Josh and Stefan, for the really exciting talk and great generating great discussions. So thank you very much, and have a great summer.
And thanks to Evgeny
Thank you.
for keeping us organized, and
Yes.
you really done a
indeed.
great job.
Thank,
Right, thank you.
thanks to
Thank you
all,
all.
and thanks to
Thank you.
Evgeny. Yeah. Thank you so
Jenny.
much.
Yeah, thank you. Bye-bye.
Jenny,
Bye.
Jenny, are you still there?
Yes, I'm still here. Yes.